All righty. Hello, everyone. Welcome to this meeting of the Warren Astronomical Society. I am Bob Trimble, your president. Do we have any first-timers tonight here? No first-timers. Okay. You can renew your membership with that man right there. And I need to do that. If anyone needs a lanyard, which I didn't put on tonight, somebody's got a lanyard. Does anybody have a lanyard? You've got a lanyard. If anybody needs one of those, get with the board and we will get it for you. So as a tradition, we like to go around the ranks and do a roll call. So I'll start with me. Hi, I'm Bob Trumley, the president. And
Amy Clark. Laura
nice. Yeah. What? Oh, hi. Well, we hope you enjoy the meeting. Hi there. Okay, so Watts wearables are purchasable from Mark Kedzier, who is not here tonight. So if you he's going to be in later.
Now graduation.
You went, oh, that's cool. So you can get Watts wearables. They are in our newsletter. We've got T-shirts and other things that you can buy, which are really cool. Astronomy at the Beach, the very Michigan's largest free astronomy event, is going to be held September 21 and 22 at Mayberry State Park, west of Northville this year. Island Lake State Park is under construction and will be closed, and we're kind of doing a theme of the sun this year for obvious reasons, and light pollution because it's so close to Northville. So the Great Lakes Stargaze is held October 3 through 6 in Gladwin, Michigan. GLAC meetings, that's the Great Lakes Association of Astronomy Clubs. They're the ones that host Astronomy at the Beach. They are held the second Monday, which is next week. So if you're interested in helping with astronomy at the beach, or you're interested in helping us advertise or whatever, we could use your help. So President, I'm sorry, they meet via Zoom. So I can get you the link, and they have GLAC has a groups.io mailing list. So if you send something to that, which I can also give you, go to all the GLAC members. So Connie and I are going to be at the Selfridge Air Show both June 8th and 9th. There are going to be a ton of GLAC member clubs at this event, and under tents and stuff. They are expecting many thousands of people at this event, and I ordered a ton of NASA swag. We'll see how much I get. Dale, you got anything? Our first VP, anything to tell the audience here? This is our first Vice President, Dale Parton.
Everyone, just to say, man, could I ever use some additional speakers? If you've got even a glimmer of an idea, okay, or if you'd like me to suggest an idea for you for what you could talk about, come see me at the break or get with me another way. Thanks.
Actually, it's not a bad idea. Just putting a list together of lecture ideas. Okay, Riyadh, is Riyadh online? Yes, he is. Hi,
Yes,
Riyadh.
ma'am.
What's going on with the observatory?
Yeah, thank you. Hello, everyone. We had our last open house on May 25th. Started out just before 7 p.m. We had roughly 60 people or so. It's been kind of the common theme. We used the 8-inch, actually it was clear that night, so we used the 8-inch refractor to look at deep sky objects and double stars. And also Jeff McLeod rolled out the 22-inch DOP and used that successfully to observe deep sky objects, and everybody loved it. So we were out there quite a bit late. We were out till about 1:12 or so when we closed the observatory. So it's been we've been lucking out a little bit, getting some clear skies. So hopefully that our luck will continue. So next open house is June 22nd, and hopefully we'll see everybody out there. Thank you.
All right, thank you. Have we been contacted by the Metro Parks yet about doing a Perseids something or other with them? I'm gonna have to get with them about that. And our picnic and open house is planned for August 24th, so that will be at that pavilion right near our observatory. So David, treasurer, what's up? David Boransky, our treasurer. I'm sorry?
All right, so treasury report. So in our checking account, we have 25,000, not $399.43. So from there, we've got lots of funding to do stuff. We got about $700 in our PayPal account. We issued out about $400 to pay for those trifolds that are going to be handed out. So those are a couple of those are in the center table if you want to look at those. And that's it. No, nothing on our credit card account, so nothing due there.
Cool. Like that. Thank you, David. All right. Charlie, our secretary, is not here tonight, and he is going to be with us later on at Macomb. Say outreach, Jeff. What's going on? This is Jeff McLeod, our outreach chair.
First, I'd like to apologize about all the cloak and dagger stuff, keeping secrets. I know many of you are uncomfortable lying to the public, but as you know, the magnetic anomaly found at Tycho crater has been identified as extraterrestrial origin. Does anyone know what I'm talking about? No? 2001 Space Odyssey? You guys can't see in internet land, but like, I mean, we're pretty much in the room. This is the exact layout. I'm Haywood Floyd. I can't help it. All right. There wasn't a lot of outreach stuff in May. I spoke at the Wayne State Planetarium. If you did something, you didn't tell me about it, and I forgot to write it in the law, so it's going to go in July. So if you did do something in May, you can still email it to me because we'll get it in the July issue. July, the big thing is the Selfridge Air Show. If you don't want to help, just come on out. It's probably going to be a good time.
Next weekend.
Oh yeah, next weekend, 8th and 9th. And then we're going to coast for a little while and take a breather until some other stuff in August and September. So that's all I have.
All righty. Thank you, Jeff. All right. Again, that Selfridge Air Show is the 8th and 9th. You can find it online. Lots of people. All right, publications. Yes. I have no idea. They're gonna point me where to go when I get to the front gate.
And you can go to one of the tabs is for weeks or something like that. You can find the map. We're going to be near the steam zone, which is kind of located in the static displays.
Yeah, I was told that they cleared out a bunker and they're making that all devoted to steam, and we're going to be somewhere around that, which is cool. And I tell you, man, nothing beat being under the wing of a B-52 down at Dayton. That was pretty cool. So, publications, is Vachaya with us tonight? Doesn't look like it. All right. So, the newsletter is up. And okay, so if you need to contact the board for anything, we are on about email at board@warrenastro.org. Okay, so getting into some astronomy news, I'll start off with my favorite. Yes. All right. Anybody that just showed up, are you first timers? No. Dale Hollenbaugh, he just showed up. Anybody? First time in the live, yeah, it was pretty cool. I like that. I like the ambiance here. Okay, so getting into astronomy news. I'm sorry. Okay, I said, yeah, let's do you, David. Go ahead and do your report.
Okay, I'm sorry to interrupt, Bob. I just wanted to say that I just saw 140 sunspots on the sun. For my quotation of this particular meeting, I wish I had studied this when I was in high school because my English teacher in high school had been so pleased about Shakespeare and time in Macbeth. But it's just in the last 5, 6 years that I've really been working on this. It turns out there are 59 mentions of the word time in the play Macbeth. And of those 59, I found 3 that are really very critical. In one, Shakespeare is really having Macbeth talk with time as if time is a person. Time thou anticipatest my dread exploits. The flighty purpose never is o'ertook unless the deed go with it. And then another one, again, Macbeth is talking to time as if it were a person. To me, you speak not. If you can look into the seeds of time and say which grain will grow and which will not, speak then to me, who neither beg nor fear your favors nor your hate. But the best one, the best one is at the very end. And he's at the end of his life. He doesn't want to stay alive anymore. And to add insult to his injuries, he has just been informed that his wife has died. And I think what he says here is absolutely spectacular. And as Shakespeare is trying to write it, he's saying, look, Macbeth has just learned that his wife is dead. What am I going to have him say? And at that point, I like to imagine that Shakespeare feels a tap on his shoulder. And he turns around, and there he sees God standing behind him. And he's a little bit surprised to see that. But then God says, Will, take a break, get some coffee, watch some video games, go to the Warren Astronomical Society Zoom section, and I got this. But I believe what Shakespeare is doing here is anticipating this theory of special relativity by approximately 3 centuries, without even having the slightest idea that he's doing it. And it goes like this. She should have died hereafter. There would have been a time for such a word. Tomorrow and tomorrow and tomorrow creeps in this petty pace from day to day to the last syllable of recorded time. And then is heard no more. And all our yesterdays have lighted fools the way to dusty death. Out, out, brief candle, life's but a walking shadow, a poor player that struts and frets his hour upon the stage, and then is heard no more. It is a tale told by an idiot, full of sound and fury, signifying nothing. And to this I add 2 more words, signifying everything. And that's what I wanted to share with you tonight. Thanks, Bob.
Thanks, David. Okay, getting into astronomy news, my favorite topic, exoplanets. All right, we have 5,638 confirmed exoplanets. That's up 22 from our Macomb meeting 2 weeks ago. We have 7,147 candidates. That's up 9. But an exoplanet thought to orbit the star 40 Eridani A turned out to be an illusion caused by pulses and jitters in the star itself. This would not be nearly so interesting were it not for the fact that this star was host to Mr. Spock's fictional homeworld, Vulcan from Star Trek. The NASA post says Spock's home planet goes poof. That's the actual NASA post, which is pretty much what happened to Vulcan anyway in the alternate universe Star Trek movie. So, yeah. So, oh, hey, stop that. Hey. Got a keyword on my screen and I don't want it. Goodness. Wonderful. Oh my goodness. There we go. Okay. The Vatican Observatory, we had a senior scientist from the Square Kilometer Array Observatory speak for our monthly full moon meetup a couple weeks ago. And the project is pretty amazing, and the amount of data that the observatory is going to be generating is simply eye-popping. And as I was looking for interesting astronomy news today, I saw that Canada has become a member of this project. And I reached out to that scientist, and he told me that Canada has been closely involved with the SKA for many years and is building the correlator for the MID telescope, the machine that combines all the signals from the individual telescopes. So in essence, a supercomputer with a specific task. So Canada is doing that. That's cool. I got an email, well, and you probably did too, Jeff, from the Solar System Ambassador rep talking about prepping for the nova in Corona Borealis. There is a recurring nova that is likely to erupt between June and September of this year. It's located in the constellation Corona Borealis, so keep your eyes peeled and be ready for a last-minute nova watch because it could happen anytime now. No, but it is P. Coronae Borealis, and that is on Wikipedia. I can put the link in chat later on. This was a pretty interesting post. Astronauts from the Apollo 17 put seismometers on the moon. Using machine learning to analyze that data from these seismometers, it looks like scientists detected regular pinging from the metal expansion on the Apollo 17 lander, something that may be useful to know for long-term missions to the lunar surface. So that article is on IFL Science. The Chinese Chang'e 6 lander touched down on the moon's South Pole Aitken Basin on June 1st. This is a sample return mission which plans to collect about 2 kilograms, 4.4 pounds of material, and return it back to Earth. Scott Manley, in one of those videos like I showed at the beginning here, talks about the mission, and there is a lunar ascent stage that will rendezvous and dock with an orbiting return vessel. That sound familiar to anyone? So the return launch from the lunar surface is scheduled for tomorrow. So that's pretty cool. Solar news. This is on the NOAA site. CME left the sun on June 1st, may begin to impact the Earth's atmosphere on June 4th. So that's tomorrow. And this was pretty interesting. The Federal Communication Commission's Public Safety and Homeland Security Bureau seeks comment on any observed impacts to communications that resulted from the May 2024 severe geomagnetic storm. So the times those auroras were here, they want to know if anybody experienced any communications issues. So that's not concerning at all. So Riyadh, any double star stuff? Do you get to view any of those?
Yeah,
At the
this is what we've been doing lately. We've been, because the planets are so close to the sun, and the moon has been also kind of not rising until very late at night or early morning hours. So the only thing that's left is either double stars, or, as you know, in the spring, the best deep sky objects are actually galaxies. And of course, for new members or people who haven't looked through a scope before, or scouts, looking at galaxies, if we've tried it, it's really difficult for them to see. So the easy thing is to rely on double stars, because those are fun to look at, easy to see. They can look at colors. And I've also even looked, last open house, we used the spectrometer filter to look at double stars, and everybody was really having a lot of fun just looking at that. It was enjoyable.
So I meant to ask you, Riyadh, would our telescope and the equipment we have be able to observe the light drop of an exoplanet transiting a star? Like how low can we go? I want to talk to you later about that.
Okay, we can.
You're laughing at me. I want to see if we can do it. All right. So, do we have any observing reports or astrophotos? Anybody? You do. 9.2, so the recurring nova 9, is that's naked eye though, isn't it? No? Oh, wow. So that's gonna be telescope only.
But the last couple actual observed were not that right. It went from like 10 to
We can see it through our scope though. Cool. Yes. But I can bring it up on the SDO. Yeah, this is the bringing up the Solar Dynamics Observatory, SDO. SDO NASA. Yeah, David said he saw a lot. So let's more images. Pull that guy up. Oh my goodness, you want the oh yeah, that one, that's better. Wow. All right, so I'm going to share that on Zoom, share screen, that guy. This is way. So that is the photosphere of our sun. Oh, it's photosphere today. And yeah, I said I got a notification of a solar flare. Yeah, I can bring it up. Oops, I do. Let's see. This guy? Yeah, this is showing the magnetic field. A lot of activity on our sun. So this is why we're seeing. Let's see the. I don't believe so. And this is a 40. I'm going to share a 48-hour animation of the coronasphere here. Of the corona here. So yeah, you're seeing this guy right here. Look at all that activity. Yeah, that's flare, 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 flare. Yeah. Wow, that was a big one. Wow, those loops are just beautiful. Oh yeah, I'm expecting more opportunities to see more northern lights. Did you? Well, I hope everybody's going to be submitting them for our calendar for next year. All right. So any other astrophotos? If not, Jeff, you can take it away. Public, yeah. You can send them to the board or the publications. They'll get there. Send them to the board. We'll get them. All right. You want the presenters here or what? No. No. That guy. From beginning. Tab. Zoom. The yeah. Get down. There it goes. All right.
Well, let me introduce a man who needs really not much introduction here. Jeff McLeod has been our president. He's been our observatory chair, and now our outreach chair. If you'd like to participate in outreach events, let him know. During his time at Wayne State University, he was a presenter in their planetarium while getting 2 bachelor's degrees, one in physics, one in astronomy. Recently started work in the aerospace sector, doing some kind of secret missile work. Um, you're gonna mount a telescope on them or something. Um, so these days, he spends a lot of time working on a space flight simulator. But tonight, he's going to simulate spiral galaxies.
Hello, hello. I just keep referencing 2001. So some of you, this is going to be a retelling. I gave this short talk last year, but we were having some internet issues, so it didn't get recorded, and I believe the people on the stream didn't get to see any of it, and it's a pretty visual presentation. So I thought I would attempt to do it again, but if you're newer, maybe you haven't seen it, and I'll bet you don't remember it anyway. So one of my favorite titles, quasi-static density wave theory. That is top tier. If you ever need to name something, that's how it's done. We'll get into it. But this is about simulating. Uh-oh, are the arrows not going to work? What if I click on it? I solved it all by myself. I unplugged it and plugged it back in. Oh, they don't need to see me. Let them see the screen. So, what am I going to be talking about? One, maybe like a misconception. How do galaxies actually rotate? What the winding problem is, which is kind of what happens with some simple assumptions. And then what is this quasi-static density wave theory? And then the simulation that I made, and then comparing those simulations to some real galaxies. This is one of those in computer science and simulating, you can often get convincing results for bad reasons. So this is not necessarily we're not saying this is exactly what's going on. And there's a lot more research in this. So this is not the round Earth theory. This is more like the impact theory for the moon. It's a pretty good idea. We're pretty sure something like this is going on, but it's not 100%. So I'm not talking about irregulars. I'm not talking about lenticulars. I'm talking about spirals. This only applies to spiral galaxies. So in the two images there, you're looking edge on the left and top down, bottom up on the right. And you can see this is a map of the Milky Way. Obviously not a real photo. We can't get out to take a picture like that. But that's what we think our galaxy looks like, similar to other spiral galaxies that we see. And we see these gorgeous spiral arms. When we're talking about like imaging galaxies, right? That's what you're there to see. So I'm gonna play this animation, and what I want you guys to do is guess which one of these is correct, which one of these is rotating the way we think galaxies rotate. Either or. The middle? So it's going to go all the way around, and then a line is going to be produced so that it's a little bit easier to keep track of the two on the right. The one on the left is spinning like an LP. It's just a solid object. Sometimes I hear that galaxies rotate like solid objects. Not saying it's wrong. All right, so now we have the lines there, and you can see the middle one is spiraling in. The interior is moving much faster than the interior of the one all the way to the right. And as this goes a little bit further along, we'll actually get labels as to what these three different rotations are. Normally, when you study galaxies, this would be a rotation curve. We would map this speed as a function of radius. And so the shape of that curve is the shape of these different outcomes. So we have solid body, Keplerian motion. That's the planets, right? Mercury goes along a lot faster than Neptune. And then what we call flat rotation. So the one that is correct is flat. Flat's right. Okay, good job, guys. So that what we mean by flat is the actual true velocity, not angular velocity, is roughly the same from the inside all the way to the outside. So what that produces is you still get a winding problem. If they're all moving the same speed, but some are closer in and some are farther out, what we're going to get is a brief period of a spiral arm. And you can imagine 2 or 3 of these, but eventually it starts to wind up too much. Okay, and now the arm is kind of lost, and it kind of looks like this flocculent galaxy. But what's going to happen here is it's going to turn into, oh, now it looks like there's arms again. And then now it looks like, oh, now there's arms again. And they went from being left curving to right curving. We don't see a lot of 5-armed galaxies. We don't see a lot of 3-armed galaxies. They are out there, but there's kind of more going on. This is not what's happening. So what is going on? So you can't produce spiral arms by simply populating a spiral shape and then letting it move forward in time. The motion of the galaxy will just mix that all up. So, density wave. We all intuitively know what this is. Okay, so this was an experiment done, I think, in the UK. They're moving along just fine, but what's going to happen is a small perturbation is going to start here, and it's going to start propagating through the system. Okay, and what is going to be established here is basically a standing wave. There's at some point you can almost track where there's a stationary car. And it's just, and you can see the motion of the cars is clockwise, the motion of the wave is counterclockwise. Okay, that comes down to the subtleties of the wave propagation speed and everything. It's not necessarily the case that it would be like that, but if you've ever been in traffic, which we all have been, I'm just going to throw this out here. It has nothing to do with astronomy, but there is a theory of traffic flow that if you try to average the distance between the car in front of you and the car behind you, you will actually eliminate these wave propagations. And if everyone did that, we would actually flow a whole lot better. But the intuition is to just be as close to the car in front of you as possible. So, galaxies do not rotate with Keplerian orbits, which is the intuition. Planets go around the sun in Keplerian orbits. So why aren't stars? So a solar system has most of its mass focused in the sun, star, whatever. And so we get Keplerian motion. The mass of a galaxy is more evenly distributed throughout the object. And so you can think of a star, like the sun, is sitting in a neutral gravitational field. It is kind of being pulled equally in all directions, ever so slightly towards the center. So if you were to perturb that star, what you would get is an oscillation around a center point. Same way as if you were to have a spring and pull on it, you get an oscillation. I should have started this sooner because it takes a second. So this is a star out at some distance. And what I'm doing right now is I'm fiddling with how hard am I going to pluck that star? How much am I going to perturb it? And it's going to oscillate around its neutral point in an ellipse.
Remind me that that is giving.
That's Jon Blum.
Morning club meeting.
John, your mic's on. Okay, so, and now what I'm going to do is I'm actually going to start the galaxy in motion. And you can see that the combined motion of this star oscillating around its neutral point and its rotation around the center. Am I I'm blocking the view? Uh-oh.
When you switch a slide,
Okay. Well, you can probably. Oh, I'm too afraid to move this. So we get a very unique pattern based on the resonance between the oscillation around the neutral point and the speed of rotation around the galaxy center. And we can make this almost anything we want. That all kind of makes sense. This is where we get a little hand wavy. Okay, we have all of these ellipses. Let's just nest them in a way that produces spiral arms. So I'm rotating each ellipsoid relative to the one next to it, and I'm going to get a convergence of lines in this spiral shape. This is that motion that the star is tracing out. Don't worry about the math. It's just there to scare you. Oh, I'm supposed to move a little bit. So very two-armed bar spiral looking galaxy there. So now these are all simulations that I created, fairly simple ones. So this is now the motion of that star in the reference frame of the wave. So in this animation, wave does not move. Wave is staying in one location, but you notice all the stars are moving through the waves. And because of their subtle movements, you get a piling up and then an expansion. Same way that a water wave, the particles aren't actually moving along that wave. The wave is propagating through the water. So you can think of the same thing happening in a galaxy. There's a wave of stars. The stars aren't necessarily moving with the wave. And we also know this is true because when we look at spiral arms, what do we see? New stars. This is where stars are born. The theory, which is somewhat supported by observations, when we get this compression of stars, we're compressing those gases and we're getting star formation. But those stars then leave the wave. They age out and die, so we don't see old stars in the waves, although there are some.
What is that? To get this to happen, what's the distribution of mass in this galaxy? Is it all in the nucleus? Is it uniform?
It's essentially uniform. I mean, you have boundary problems. So this is a great question, and why I said we can simulate or emulate things that get us what we want, but aren't really the thing. So far, I have not mentioned gravity. There's no gravity in this calculation. So it's very hand wavy. It's just, we kind of assumed that if we were in a pseudo-uniform field, we would get this oscillating motion. Obviously, that's not really the case, and it's less true in the core or at the edge of the galaxy than it is at the center or at the midpoint. So when you try to do galaxy simulations with gravity and billions of data points, you break computers. So there's very few that are actually running the physics to try to figure out what the galaxies are doing because it's so hard to get enough of the population of a galaxy. I mean, oftentimes, so if you can see my image here, there's like maybe 1,000 stars there. So each one of those would have to represent a billion, 10 million stars.
With a billion.
Right. But yeah, so far, we're really just from somewhat first principles just saying, this kind of stuff makes sense and it's analogous to what might be going on, but to actually try to, I mean, and people are doing it, don't get me wrong. I just am not capable of doing those kind of simulations, and the math gets way more complicated than I'm willing to deal with.
The galaxy stay together.
For sure.
What about repeat the question?
Does the galaxy stays together from gravity? Absolutely. Or dark matter. So that's another great question. So he's asking about barred spirals, if we've ever seen images of barred spirals, which we sometimes do think that the Milky Way is a barred spiral. I think that's the general consensus. when I was in my galaxies class, that was one of the most open-ended things in galactic formation. We know almost nothing about bars. What forms them? How stable are they? Are they long-lasting features? No idea. Why don't we see squares? No idea. Yeah. Not the subject of this presentation. So now this is in the rotation frame. So now you're kind of standing over the galaxy, and as it rotates, you're rotating. So now in this frame, you just see that undulation of the star around its balancing point. And now the waves are what's moving around. And these just get hypnotic the longer you look at them. So now we put this both together, we get the absolute frame. This is now looks more like what you would expect to see. The galaxy is rotating, the arms are rotating, and the star is tracing out a pseudo-elliptical shape. Right? Cool. That's what I wanted. And then we fiddle all the parameters to make it look exactly what we want it to look like, and we get the grand beauty of, but still just a handful of stars. So this was all done in Desmos. It's a free graphing calculator. It's pretty rudimentary. So now that I had the mathematics, I put it into Python. And what I can do with Python is I can randomize all of these things because, a galaxy is not going to be that structured. So let's populate this and say, well, kind of move the stars around and adjust their sizes and make them more like what we would see in a galaxy. And you can get something like this. Which for a bunch of hand-wavy mathematics that doesn't even involve gravity is pretty darn good. It looks like a spiral galaxy. Again, this might be going on, but it's not exactly this. So here's another one with this like forked spiral arm. Kind of pretty. This is now like maybe 1 million stars. So now I'm just making galaxies and pulling up images of galaxies and going like this. Which one looks like the same thing? These kind of look the same. Again, not proof of the theory, because you can really fake anything you want at a certain point. Whoops. M74. M100. So another thing I can do because of all these different parameters, I can fiddle with these numbers to get asymmetries. So if you look at the simulated galaxy on the left, it's not a mirror image from one side to the other. This is kind of diffusing out. This is, it's wonky, which is what you would expect to see. And you can also get different numbers of arms. So where the theory kind of breaks down is you can get anything you want when you have the math. I can get 3-arm spiral, perfectly symmetrical 3-arm spirals. As far as I know, I've never seen one. There's some weird galaxies, but they're usually the results of like mergers and stuff. Kind of like a bar.
There's some correlation between the duration of the rotation and the observable galaxy.
So that's the other problem is when we look at galaxies, we can't see this happening. It takes tens of millions of years to watch a star migrate out of the wave. And how long for the entire human history we've existed for what, a 20th of a rotation of our galaxy? So yes.
Now
You can get anything you want. Yeah, you can fudge the numbers. There's it's also kind of, it can go out as far as you want. You can spiral it in much tighter than you would ever be able to in real life. So yeah, you can even get cold galaxies. Yes.
You can use number shells to measure one element in the velocity of sound is very close.
Hmm.
And also the data measurements in the data signal to be pretty much motion of bigger pieces of the galaxy.
Yeah, it'll probably, so if you're unfamiliar with what he's referencing, so we can, because we know these rotation curves for other galaxies, we can look at stars in other galaxies, see those radial velocities, and get an idea of how they're rotating from inside to outside. But we can't see the wave because again, just like a water wave, the particles aren't actually doing the motion. So if we're looking at the Andromeda galaxy and we see a spiral arm, we can measure the stars in there moving, but we can't see if the wave is going forward or backwards. Is it moving at all? Is it a standing wave? We don't know. And then the other thing he referenced was the Gaia data. I'm guessing over the next 20 so odd years, when we can actually put pen to paper with a lot of the Gaia data, we'll start to learn a lot more, at least about our own galaxy and how it's actually moving. But I haven't actually heard, well, I don't keep my finger to the pulse as much as I used to, but I haven't heard any groundbreaking, you know, oh, we now understand X about.
The data of what and it's show this number of you.
Yeah, we're constantly evaporating stars. And then this just, if you look at it long enough and then you look at something else, everything will rotate in the opposite direction. So that's the whole kit and caboodle. I would love to make that other image an animation, but that galaxy with a million stars takes my computer like 5 minutes of computations to produce that one. So if I want to make a 10-second animation, it's like a day just letting my computer chug. It's old. I just don't want to do it. This was bad enough. This took like 5 hours. So
Where'd the mouse go? There we go. All right. Okay, share. All right, everyone. So now is when we typically take our snack break. So let's give it 20 minutes. So that would be at 10 after 8. So take a break, get a bio, get a munchie, and be back in 20 minutes. Hey, Bob, any pictures to show?
Nope, no pictures. I, I will be showing some at the Thursday meeting.
Claritin Clear? Yeah, fast relief from allergies with nasal congestion so you can breathe better. Claritin plus decongestant. Live Claritin Clear.
Type 2 diabetes? Discover the Ozempic Trizone. I got the power of 3. I'm lowering my A1C, CV risk, and lost some weight. In studies, the majority of people reached an A1C under 7 and maintained it. Also, there's known heart disease. I'm lowering my risk. Adults lost up to 14 pounds.
I lost some weight.
Ozempic isn't for people with type 1 diabetes. Don't share needles or pens or reuse needles.
That was a view of our audience here in the library, where we would move to the library because we're not in the auditorium tonight. And I actually kind of like this. All the books is really cool. 4-minute warning. Jeff McLeod is having a discussion with some member of the audience here talking about Forbidden Planet. Say what? I am not. I'm muted. What's that? Testing, testing. Huh?
I can hear you.
It's picking me up. You're not hearing me? Testing, testing. Okay. All right. So yeah, the thing. Jeff McLeod is having a discussion with a member here about the movie Forbidden Planet. If you've never seen it, you ought to see it because it's fantastic. So we are 2-minute warning.
Hey, Bob, how many people are in the audience there live?
$25. You're out. See you. In 1 minute. Okay. Wife and I and daughter and granddaughter will be there on Saturday. I think we're gonna get there about 6:30. All right, I'll tell her that. That might not be a bad idea. All right, it is just about that time. Okay. All right, 10 after. Here we go. He used to have one of these. This is my wife's. It's written on it, the Thunderer. Okay. Want to take it away?
Okay. Most of the people here know Jon Blum, longtime member of this organization, past president, past first vice president of this organization. He couldn't be with us tonight. His granddaughter, Rebecca, has spoken to us a number of years ago when she was going to some kind of space camp down in Florida with NASA. Well, she has continued that interest. And I'd like you to hear that story tonight. Unfortunately, she couldn't be here with us, but we have a video of her speaking. This video was made at Fox Run, where Jon and Rosie Blum live, where she spoke about her story of trying to become an astronaut. So this video we're going to see was made in August of 2023. Rebecca Blum, is just graduating from Brown University in Providence, Rhode Island. I almost wound up on the faculty there once upon a time. Could have, but I didn't want to do it. She has been a pre-med student for the past 4 years with a major in biology. She is about to take a quote unquote gap year between college and medical school, during which time she will work as a trainer for emergency medical technicians on the Brown University ambulance system for the summer. Then she's going to move temporarily, she gets around, temporarily to California in the fall to do research for NASA at their Ames Research Center. She does not yet know which medical school she will go to, but that will start in September 2025. So her topic tonight is called Analog Astronaut Training. What you're going to see is Jon Blum first introducing her at Fox Run, and then you're going to see her talking, okay? Let's roll it. All right. The video up here. Go share that. I do not need to see anybody's face from this. How to make that go? There we go. All right. So here we go. What? Why are you doing this to me? Wait 1 second. We're having technical issues. Ah. Our drive filled up, so I gotta clear some stuff away out of here. There we go. All right, so let's share that. It's a Zoom, come on. Here's my Zoom Bob. Share screen. There, share. All right.
Video of last month. Next, we're gonna have my granddaughter tell us about some astronaut training. My granddaughter Rebecca has been looking through my telescope since she was 4 years old or younger, and always was fascinated by the stars. When she was 7 years old, she and I were talking about the astronauts who had been to the moon back in 1969 and 72 when we sent astronauts to the moon. And it came up in our conversations that only men had been to the moon, so this was shocking news to her at age 7 that we don't send men to school. So she immediately drew this picture showing herself as the first woman on the moon, and has been working towards that goal, or maybe going to Mars. Now, we've learned at a past Astronomy Club meeting that the planets are moved in different positions. We have the sun on the left, and we see the first 4 planets, Mercury, Venus, Earth, and Mars, are very close together near the sun. And then the other planets, Jupiter, Saturn, Uranus, and Neptune, are spread much further apart. So I'm going to show you a lecture about this subject that Rebecca gave when she was a little younger than she is today. So even though I've seen this video a few dozen times, I'm still scared and nervous when she runs across the street. Well, she's gotten a little older since she made that video. Now she's a senior in college at Brown University in Providence, Rhode Island. She works also as an emergency medical technician on the Brown University ambulance system. She would like to become an astronaut physician. And she recently participated in a simulation of astronauts on the moon. And that's what she's going to tell us about today. So here is Rebecca. Someplace is Rebecca.
Hello, everyone. Thank you, Grandpa, for the introduction, and thank you all for having me here today. Can everyone hear me in the back? It's okay? Okay. Okay, perfect. It was a misty morning when the Eagle crew landed on the south pole of the moon. As they entered their base, they experienced a loss of communication, unable to reach Earth for over an hour. The upcoming week brought even more challenges. They performed CPR on a mannequin during a spacewalk using a new technology that gives compressions through a spacesuit. They were then woken at 2 a.m. to the sound of alarms indicating a solar flare emergency. This adventure took place last month during a lunar simulation, and I was on the crew. This simulation was with the program Asclepios. Asclepios is a simulation, also known as an analog mission. These missions don't actually take place in space. It's important to understand these missions are on Earth, but they simulate going to space very well. For example, they often take place in places that could be the lunar or Martian surface. They look very similar. So, for example, they could take place in the desert or near a lava flow or in the mountains. There's often crews of analog astronauts during analog missions, and these crews live in constructed space bases that look and feel very similar to real space bases. The crew often communicates with a mission control center, just like real astronauts do when they go to space. It's important for these simulations to be very realistic, and that's because these missions are an important avenue to test research. They test space research. Research is a lot cheaper and safer to do on Earth than in space. So if there's any projects that can be done on Earth, even when in space research, they are done on analog missions. For example, maybe we want to test a lunar rover that'll soon go to the moon. We could test that first on a lunar analog mission. Or maybe we want to see how human interactions change over the course of 3 months in isolation. That can also be tested on an analog mission, but it's important that the missions are as realistic as possible so the research is the best it can be. Now, these missions are also good for professional development. A lot of people go on analog missions in hopes to gain the skills they can maybe use in the future as an astronaut. And astronauts, after going to space, also take part in analog missions for research. NASA has 16 analog missions that it uses for research. In the top photo, that's a picture from one of NASA's analog missions called NEMO, which is off the coast of Florida, and it's a diving analog. And we'll discuss later why it's good to practice diving and why diving is a good simulation for space. In the bottom image, that's another NASA analog called High Seas, and it's in Hawaii. Now, analog missions don't have to just model the mission. They can also model the astronaut selection and training, which means that the selection process for the mission and the training looks like that NASA does. And it's not always common that there's a selection and training component. But the analog mission I went on with Asclepios did have an extensive selection and training, the longest I've ever seen for an analog mission. Our selection process was 6 months and had multiple phases, just like NASA selection, and our training was over a year. Asclepios is also special because it is the first and only student-led analog mission. That means that all the analog astronauts are also students, and it means that everyone who puts on the entire mission, all the teams, even the head, they're all students. And it really underscores what is possible for students to put on and perform. So before I go more into Asclepios, I'm just going to give a little bit of background about myself. My grandpa gave a great introduction. I've always wanted to be an astronaut. I fell in love with the night sky while looking through my grandfather's telescope when I was just a few years old. And as I got older, I realized I also love science, especially biology and medicine. I'm currently a rising senior at Brown University studying biology in hopes of then going to med school to study space medicine. I want to be an aerospace physician. And then I will apply to NASA to be an astronaut. I'm currently pursuing my passion for medicine. I am an emergency medical technician, or an EMT, on an ambulance back at my university in Rhode Island. I also do research at NASA Ames Research Laboratory, studying how drugs can be developed for long duration space missions. So I was introduced to Asclepios from one of my friends who was on the second mission. I was on the third mission. There's a mission every year. Asclepios takes place in Switzerland, which means I moved out to Europe for 7 months for the last half of the training process. It's a 2-week analog mission, which means we live inside a military bunker deep within the mountains in Switzerland for 2 weeks. Asclepios has a focus on research, just like all analog missions. Its focus was on space medicine this year, which was perfect for me. Space medicine is the study of how the human body changes in space and how we can best mitigate those changes. So the research projects that we brought onto the mission investigated questions in space medicine. And a lot of our trainings throughout the year had a focus on space medicine. Another focus for Asclepios is preparing the upcoming generation for work in the space field. Because the organization is entirely made up of students, it allows us to really see what goes into a space mission, from the selection to the training to the mission itself. It's something we can't get from a textbook or something we can get from a speech. We have to go out and do it. And we learn so many lessons while doing it. And as I mentioned before, there's a selection and training process, and it was carefully planned so that would mirror that of NASA, the European Space Agency selection. In this top photo, that's an image from inside the military bunker, deep within the mountains of the Swiss Alps. So, as I mentioned, Asclepios is a student organization. The core group of students is comprised of 40 students ranging from the bachelor to PhD level. And the students are from 5 continents and 22 different nationalities. There's also 5 main teams that make up Asclepios. There's the management team, the science team, the medical team, the astronaut team, and the design team. As one of the analog astronauts, I was part of the astronaut team, but I also later became part of the medical team too. So the crew of analog astronauts, there were 10 analog astronauts total, and they were from all over the world. There was 1 other American, as well as students from all these countries here: Italy, Switzerland, Portugal, the UK, Germany, Spain, and France. Everyone was a student from the bachelor to PhD level, and at the time, 10 astronauts were recruited, and 6 ended up going on the the mission inside the military bunker. So you're gonna end up with a crew of 6. The other 4 analog astronauts are capsule communicators, also known as CAPCOM. I'm going to be teaching you all a few technical terms today about human spaceflight, and you all can tell your friends after, and you'll seem so knowledgeable about all these different terms. And one of the terms is CAPCOM. As capsule communicators, they work in mission control and are the main way that astronauts communicate to the rest of the world. So let's say an astronaut has a question about their research project, and they want to get in touch with the head of science within mission control. They first go through CAPCOM, the capsule communicator. It's very realistic that the capsule communicator is from the astronaut crew. In real life, the capsule communicator is often an astronaut. They know what it's like to go up in space, and they've done training with the rest of the crew. So they can best communicate what the astronauts may be feeling or seeing, and they can communicate with mission control. So again, there were 6 in the base, and then the other 4 are going to be CAPCOMs. So after our selection process, we all met each other and launched into our year of training. The first half of the year had a lot of Zoom calls and online trainings where we brought in guest speakers to teach us things from space medicine. We had Russian language trainings. We had trainings about public speaking and how to deal with isolation and confinement. The next half of the year had in-person trainings. So we went to Switzerland and Italy, often for trainings, and I'll go show you all what those trainings looks like. Now, I want to draw your attention to the bottom right. That's a photo of us doing a fitness training with an Olympic judo coach, and she was also a FIFA soccer coach. Her name was Esther, and she had us do a lot of fitness tests together. All of these trainings that we did throughout the year tested us either physically, emotionally, or cognitively. We were pushed to our limits, which meant that during the mission, we were prepared for anything that came our way, and we were prepared to work together as a group. So our first big training we did was the extreme environment training. This training was a camping trip in the Swiss Alps for 5 days in the winter. The 2 main points of this training, the first was to discover our natural roles of the team. During this training, we did not know which astronauts were going to be inside the base for the 2 weeks and which astronauts were going to be the capsule communicators. So not only were we dealing with the cold weather and everything that comes with camping, but we were also being evaluated throughout the 5 days. This also models what astronauts may have to go through, as all eyes are on them when they're on the International Space Station, and they may feel pressure to perform when they're on the International Space Station. And even within the 6 base astronauts, there's also positions that the astronauts can have. There's the communications officer, which is in charge of the microphones and getting in touch with mission control. There's the science officer, which is responsible for all the science projects that we do on the mission. There's the health officer. There's actually 2 health officer roles, and they're responsible for the astronauts' health on the mission. And I was one of the health officers, but I didn't know it at the time during this training. There's also the base engineer, which is responsible for taking care of the base. If anything falls apart, they'll fix it, and they know the entire inventory of the base. And then last, there's the commander, which is the leader of the astronauts. So we were also, they were evaluating us to see which role would be our best fit during this training. The second half of the extreme environment training was to build our physical and mental resilience. It was definitely cold. In the Alps. So we slept in temperatures below 0 degrees Fahrenheit. Your hands and feet are frozen the entire time. They go numb within a few hours of arriving. I actually lost feeling in my left toes for 5 weeks after returning back home. But the feeling eventually came back. But it was definitely intense, but it was great, a great way to build our resilience. We also went ice diving. Yeah. Ice diving is great because it teaches you how to perform with your life support system on your back. So you have oxygen on your back, just like how astronauts have oxygen on their back during spacewalks in space. It's also great because going underwater in water submersion in general stimulates microgravity really well. You may recall, or you may have seen astronauts when they're training for NASA missions or missions at the European Space Agency, they have their spacesuits on and they're underwater. And that's because you feel weightless, just like how you would in space. So those are the reasons we did this training. In the bottom photo, that's me giving a thumbs up before my first dive during the day. We also went diving at night. When we went diving at night, it was completely dark and it really didn't feel like you were in space. The other photo is me with my friend Luke, who later became the commander or leader for the mission. Now, we went diving in a frozen lake. So we first had to dig holes in the lake. You can see the photo to the left. There's the mountains and then a flat sheet of snow. That under that flat sheet of snow is the lake. The ice covering the lake was about maybe a foot deep, and we used shovels and drills to dig into the ice. So to the photo on the right, that's me with a drill. I did this movement and drilled into the ice, and then we would take some saws and shovels and make these giant holes. And now the next slide is exciting because you all get to see what it looks like underwater. You can see that there's some light still. When you're under the water, you can see when it's during the day, but at night it is very dark. You can also see the sheet of ice that's above us as we go diving. When we weren't busy diving, we were back at base camp. When we were at base camp, we had important jobs we had to do. One of the most important jobs is making sure there's enough fresh water to drink. So we would go down to the lake, we'd fill giant jugs with water and drag the jugs back to boil the water. Boiling the water sterilized the water so it was safe to drink, and it also provided a little bit of warmth. We would drink the hot water throughout the day, and we would put the hot water in our freeze-dried meals. And this was the only bit of warmth that we got, so we enjoyed it. So in the picture to the right, your left, you can see that's me with my friend Pietro, who later became the science officer, and we were on boiling water duty. And when you're on this job, you do it the entire day. There was about 20 people at base camp, and everyone is thirsty and likes to drink. So the second you finish boiling water, someone's already drinking. So you keep boiling water throughout the day. When we weren't doing those jobs, we did team building exercises. We built an igloo that we actually got to go inside. We would do exercises like building a tent blindfolded or starting a fire. And during this time, they also wanted to see how we interacted as a crew. Here's some last photos just because they're so beautiful. And this is dusk setting in over the camp. And then the other photo is me with two Arctic explorers, Alonashan and Vincent. And I mentioned that Asclepios is all students. We did hire these two explorers to lead the expedition for us. And they're also diving experts, and they took us diving. The next training we did was the 0G training. G stands for gravity. So all of us on Earth right now are experiencing 1G. When you go on a roller coaster, you may have experienced 2, 3, maybe 4 Gs. It feels like your head is getting pushed back or your hands are flying back. Or maybe it's when you're in a car accelerating and it feels like you're being pushed back in your seat. That's because you're experiencing more than one G. Now, if you go the other way to zero G, it feels like you're weightless. And that's what astronauts experience when they're in space. So what we did is we went in a Cessna plane and we did parabolas, which is this movement, like that. And when you're around here, you begin to experience weightlessness. Weightlessness, weightlessness, just like that. And in this image to the left, you can see it says 20 seconds of microgravity. Our plane was smaller, so we didn't get to 20 full seconds. We spent about 5 or 6 seconds in microgravity, but we did, or in zero G, we did do 5 parabolas. Now, this wasn't just so we could experience the weightlessness. We also brought projects on board the plane. So sitting next to me is my friend Max, who later became the base engineer, and he's wearing a virtual reality headset, which was testing how being in zero G may affect our spatial awareness and our orientation. And then one of my other friends brought a project looking at how menstrual blood and menstrual cups may react to zero G. In the front is my friend Pollock, who later became one of the capsule communicators. And this is actually a video. So you'll see zero G, us experiencing zero G. So I have a stuffed animal I'm throwing around. If we were in no G, the eagle plush would fall to the ground. But because we're in zero G, it floats around. So I'm gonna play that video again.
Anything is incredible from Kerbal Space Program.
Now, we also had a medical training because the theme of this year is safe medicine. Because I'm an interest in medicine, I also joined the medical team. And I gave a lecture about how to perform CPR. In the photo to the right, that's a couple of friends performing CPR on a mannequin. In the middle, that's the head medical doctor, Jess, teaching me how to suture. Now, Jess had a medical degree, but she was also still a student getting her PhD. We also had research trainings because there was going to be projects that were brought onto the mission. These photos are pictures of me giving a training for one of the research projects that me and my friend Rocio brought onto the mission. Rocio was another analog astronaut who later became the capsule communicator. Our labs were looking at a new way we could produce drugs for long duration missions. If you think about it, many drugs, especially protein-based drugs, may expire within 6 months. But if you have a mission that's 2 years, 3 years, those drugs are going to expire. So you need a way to produce those drugs on demand in space. Because we were looking at protein-based drugs, we could take the DNA sequence for the protein and then put that sequence in bacteria or other systems that will produce the drug for us. And then we isolate and purify the drug on the mission. So that's us teaching the astronauts how to work that system. We also did a dress rehearsal training. This training is super important because it makes sure that everything is sorted out before our real mission. The dress rehearsal was only 2 days long, but we tested out the standard operating procedures. That's another word for all of you. The standard operating procedures are the instructions that we follow for the mission. And they cover just about everything from how to wash your hands to how to brush your teeth, to what to do if you lose communication with mission control, all the way about what to do during a solar flare or fire drill. So we have these standard operating procedures up on our computers and we reference them throughout the day. After a year of training, it was time for the mission. This is the 6 astronauts that were selected to be inside the base for the mission. To the top left, that's my friend Max from Germany, and he was getting his PhD, and he was the base engineer. In the middle back, that's my friend Matisse. He was from France and had just finished his master's degree and was the communications officer. In the top right, that's my friend Pietro from Italy. He is getting his PhD and was the science officer. In the bottom right, that's my friend Luke from the UK. Who's getting his PhD. It was the commander or the leader. I'm in the middle at the bottom, and I'm from the US, and I'm getting my bachelor's degree. And then I was one of the health officers. And next to me is my friend Sam, who just finished his bachelor's degree, and he's from Switzerland and also was one of the health officers. So now I'm going to show you some photos from inside the base. The first photo up is the bathroom. You can see there's a toilet, and then we have a curtain that we could close for some privacy. And there's also a sink that did have running water, but we did not use the sink faucet during the mission. We wanted to conserve water and use hand sanitizer, just like how astronauts do on the International Space Station. There also was a shower that we only used once, also to conserve water. So I had my shower on day 11. They had the boys shower first. I don't know why. They were a few days before me. Maybe they thought they needed it a bit more. This is where we slept. So we slept on these, I guess, cot/beach chairs, and we slept in sleeping bags. And there were 4 beds in here and then 2 beds in the other room. And we like to say that, you know, 6 beds wouldn't fit in this room, so we have to put 2 in another room. But one of the astronauts snored very loudly, and they slept in the other room. This was our kitchen, which was 2 tables, and then the food was pretty clever food. I'll show you all a bit later what that food looked like, but it came in these cardboard boxes out under the table. And then the silver contraption in the back was filled with water, and it would heat up, and we poured it into our food. And then the carboys with the red top, those are filled with water, and that's where we got our drinking water during the mission. Now, this table right here is where we had our meals, and then the table behind it is where we put our computers, where we could reach mission control by our computers, and also the computers had standard operating procedures that we would reference throughout the mission. This was a hallway, and I'll take you down rooms in the hallway. This was our sports room, so we did fitness every day to stay in shape, and I'll touch more on that later. One of our science rooms, there were more tables in the room, and each one had a different experiment set up on it. Another science room with experiments. This was our fun rec room. I know it looks super fun. We had a couch that we could blow up with air. The arms of the couch popped, so we didn't have arms, but we did have books and card games we would play in there. Now, I've been mentioning Mission Control Center. This is a picture of Mission Control Center. Now, Mission Control was not inside the bunker with us. It was located in a different area, just like how Mission Control is back on Earth when astronauts are in space. The main roles of the Mission Control Center are Flight Director. Flight Director is responsible for how the overall mission goes. There's also the Biomedical Engineer, which is the head medical doctor, as well as Capsule Communicator, or CAPCOM, Procedures, which deals with the flight plan, and Contacts, which is responsible for contacting media. This is our schedule for one day in the base. This is just one day. So each astronaut is indicated like in a column down. So for me, I'm the blue column down, and we start around 7 a.m. and then we finish at around 12 a.m. That's when we go to bed. So pretty packed days, and most of it was doing research and we would reference the schedule throughout the day to see what we had to do. Just like how astronauts on the International Space Station have structured days that they follow. I mentioned that research is an important part of analog missions. So in the photo to the left, that's me working on the astropharmacy research project, which was the research project me and Rocio proposed to do the looking at how we can produce drugs for long duration missions. And then the middle photo is the project called hydroponics, which was looking at how we could grow plants in different conditions with different amounts of water. And then we had 8 other projects, so there are around 10 projects total. Here is a video of me with Luke, who is the commander, doing the astropharmacy project inside the base. You can see that it's not a traditional lab space. I showed a photo earlier of our lab trainings inside a research lab, and that was much cleaner. This is just on a table near the bathroom. Show the video again for you guys. It's a time-lapse video, so we're moving extra quickly in this. It's sped up. We did sports every day, which is just fitness to keep us in shape. Astronauts usually exercise for around 2 to 3 hours in space because the microgravity degrades their bones and muscles. So we too exercise every day, and we had a sports plan that we followed that had instructions about what sports to do. This is the food we ate. So the photo to the right is pasta with tomato sauce, which was our favorite meal. This is the best that it got. We fought over this. We would trade pasta tomato sauce like currency in there. We had a menu that told us which food we were getting for the day. And then it was freeze-dried, so we would heat it up with water. And I'll show a video of that. So here's the pasta with tomato sauce again. We fill up the package with hot water. Then we mix it a little bit, make sure water gets to the bottom. And then we seal it. And then in 10 minutes, it's ready to eat. Astronauts in space also have freeze-dried food. That's to reduce the weight of the food. Now, how do we brush our teeth? For most of the mission, we used something called tooth tabs. This is just a stock image, but our tooth tabs look very similar. You put the pill in your mouth and you chew it, you switch it around, and then you can swallow it, but it usually tastes so bitter and gross. We ended up doing what my friend Pietro is doing in this picture, which is spitting it into the toilet. And we would do this twice a day. Now, we also went on extravehicular activities, also known as EVAs. This is another advanced space word you all will know by the end of this presentation. An extravehicular activity is a spacewalk. So we went out in spacesuits, and these weren't real spacesuits, but they felt very similar. They weighed about 40 or 50 pounds, and that weight was on our shoulders and our back. So it was pretty uncomfortable. Here's a video of 2 astronauts performing a spacewalk or an EVA to take down our weather tower. Our weather tower collected real weather data throughout the day that we could bring back to the base and analyze. I think all of us have a pretty lovely relationship with these EVAs, and that's because, for one, we loved being able to change up our routine and go outside and see the sun. When I did my EVA, it was day 11 for me, and I saw the outside world for the first time. So that was nice, but these suits are, again, very uncomfortable. The visor fogs up. It's hard to communicate. So you don't really feel like you're outside necessarily. And after maybe 2 hours or so, you're ready for it to be done. And the EVAs would usually be between 2 to 4 hours. I also want to mention that all these videos in the base were recorded by the astronauts. There was not a film crew there. We did not interact with any other humans during the mission. We just saw each other. And we filmed these on our own cameras. So it was overall a mission success. We did all of our research projects and everything ran really smoothly. Before I get to questions, I'm gonna make sure we have enough time.
Let's do questions at the end of the hour, since we're short of time to do it right now.
Sounds good. So at the end, if anyone wants to stay, I'll answer any questions. Enjoy.
Thank you, Becca.
Video. This is not the people we had thought now. It was kind of a different kind of thing, but it's kind of related. I thought this would be important.
Yeah, Rebecca Blum is pretty amazing. She talked about going to a couple different space camps to the WASP like 2019. And when COVID hit and we did astronomy at the beach virtual that first year, she allowed us to use those videos. We did a whole children's program, so her videos were highlighted on that. But yeah, I want her to be a mentor for my granddaughter because she's freaking amazing, and she obviously has very good communication skills in front of an audience there. So
Thanks, Bob. Thanks for all the kind words, Bob.
Oh, your granddaughter is amazing.
Yes, I think so too.
Does anybody here have any John? Anybody have any questions for John? You might be able to answer something. Okay, well, if not, well then oh heavens, where's my phone? Should have that out.
I have a question for this. Is that temporary event activating going to space?
Ken Burton asked, is the kind of training that your granddaughter went through required before astronauts go into space? I'm going to guess yes.
That specific thing she did isn't required, but they're required to have done had a lot of experiences that show that they're interested and that they're prepared and that they are serious about wanting to become astronauts. I think a lot of people just think, oh, gee, this would be fun to fly in space. But she's got a long list of experiences already that she can show that she's been interested since she was a kid. She went to NASA Space Camp every summer during high school. She went to Possum Space Academy, which she gave a talk about here a few years ago here at WAS. And she's worked as an emergency medical technician on the Brown University ambulance system, which is towards her career in emergency medicine, which is what they would want for a space physician, is training in emergency medicine. So she's trying to accumulate things to put on her NASA application someday. And she's doing some research for NASA at Ames Research Center in California next year, or in a few months. So these are all things trying to build up her resume so that it'll look good. Obviously, they have way more applicants for astronauts than they've got positions for astronauts. So I hope I live to see her become an astronaut.
Yeah, if she ever launches, I want to be on the ground watching.
I want to be up there with her, but that's not going to happen.
Yeah, me too, but that's not happening. All right, so if that's it, our next meeting will be in 2 weeks, Thursday, June 20th at Macomb Community College. Our next star party will be 2 days after that on June 22nd at our observatory. And we meet after this at the Redcoat Tavern on Woodward, north of 13 Mile Road. And with that, we're closed. Good night, everyone. Clear skies. Leave it stuck up. We made it.